Hi. In my last video, I was discussing how to make John Conway's game of life apply to images, how we could see the game of life in colors. And obviously, we succeeded at doing that. However, there was a problem that I didn't discuss with you in the last video. And that problem is simply how long it takes to run the game of life. So here I attached a profiler, or I ran a profiler, for 10 frames of the game of life, 10 frames of this Trump image. And the profiler said it took 113 seconds. In other words, it's taking a really long time to create the game of life images. And you can see where most of the time goes. Most of the time is in our isAlive function and our neighbor count. In fact, the total time we spend in these two functions is about 108 seconds. That's 108 seconds out of 113. So we're spending almost all of our time counting neighbors and checking to see if cells are alive. So in some sense, you may be surprised that it's this slow to generate a game of life image. And I want to talk for a second about why that is. And it's because as we implemented game of life last time, what you have to do is just for each cell, you're getting the neighbor count. And you say, how many neighbors do I have? And to check that, you say, well, how many people do I have here? Do I have a cell here? Do I have a cell here? Do I have a living 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 cell there? And that's for one cell. And then you've got to do it for the next cell, the next cell, the next cell, and so on for all the cells. And remember, these are 256 by 256 images. We have to not only do that for each pixel, but we've got to do it for the red, for the green, for the blue, and then we have to do it for each frame. So it's quite multiplicative. We're getting a relatively large number of computations that we have to do, and that's why it takes so long. So a kind of naive approach might be to say, well, we spend almost all of our time in the neighbor count and isAlive function. Maybe we could optimize those functions. So that'd be kind of the naive, or like, okay, that's a basic idea. How could we improve the performance? But when I tend to think about optimization, I think of the saying that the fastest code is the code that doesn't run at all. In other words, if we looked at these functions and we tried to figure out, well, how could I make this 10% faster? How could I be a bit smarter about my neighbor count or something like that? How could I improve the neighbor count function? We might be able to, make neighbor count 10% faster, 20% faster, something like that. But if we took a different approach and just asked, how could I not do neighbor counts at all? How could I call neighbor count less and call isAlive less? Then, rather than saving the 20% or 30% of speed that we'd get from our performance gains, we'd be saving 100% because we wouldn't be calling it at all. And so that's obviously a lot better. So if we go back and think, well, how can I neighbor count less? That's going to give us an answer for how we can improve the performance. Now, in some sense, neighbor counting is necessary to produce the next frame of our game of life board. Obviously, we have to know the number of neighbors. We have to know how many people are here and here and here in order to say what this frame is going to be, or what this cell is going to be next. And so the way we can do that without doing a neighbor count for every cell every turn is we can just keep track of the neighbor cells. And we can keep track of the neighbor counts separately. So we can have this, parallel array where we just say we'll do the neighbor count once for every cell at the beginning. You say this is 2. There are 2 neighbors here. Oops, not there, obviously. There are 2 neighbors here, this guy and this guy. So we put a 2 in our neighbor count matrix. This guy has 2 neighbors, and so on. So we can kind of fill up our neighbor count array. And when we do that, when we're going to update and produce the next frame, we just know that this one should have life, this one should have life, this one should have death, this one should, die, and so on. We can do that without doing a neighbor count for every cell because we've already done the calculation. And the other thing to know is that when we do something like say, okay, a cell should live, there should be life at this cell, in order to avoid doing more neighbor counts in the future, what we're going to do is we're going to look and say, is this cell currently alive? Well, no, it's dead. It should be alive. It will be alive in our next frame, but it's currently dead. So what we're going to do is just increment all of the neighbors of this cell. So we're going to say, okay, you guys should just increase 2, 3, 3, and so on. So that way we never do that kind of expensive computation of looking at all 8 neighbors and adjusting them every step. Instead, we only do an update when a cell changes. If this cell was already alive, so it should be alive and it's already alive, then we wouldn't do anything at all to our neighbor counts. So we wouldn't make any updates. Conversely, if it was already dead and it should be dead, then we wouldn't make any changes. Or if it's going to stay the same, we're not going to make any changes. And so then there's one further way we could optimize this, which is we could just keep track. So rather than updating our neighbor counts whenever we know that we should, whenever we make a living cell, a dead cell alive, rather than update the neighbor counts then, what we could do is just keep track of a kind of collection of neighbor counts that we need to update. So we could say, let me write this slightly differently. We could just say that 0, 1, that's a key that needs to increase by 1. 1, 1, we need to increase the neighbor count by 1, and so on. And the reason we would do it this way is because it's possible that, this cell is going to change, and this cell is going to change, and this cell is going to change. And so we can just accumulate, this will go up to 2, to 3, maybe this one drops to 0. We'll just accumulate all the changes we're going to make in our updates collection. And then we'll apply our updates back to neighbor count. And that's just going to completely obviate the process of checking all my neighbor counts. So let me just quickly show you what that looks like when I implemented it. A couple changes I made. One to my die, life, and stay function. They're now returning a tuple rather than just a number. And what the tuple is the tuple, the first value is what we want the new value to be. And the second value of the tuple is going to be the increment. So that's going to be, you should change my neighbor count by this value. So with the die method, you should change the neighbor count by -1 if the pixel is currently alive. Otherwise, don't change the neighbor count at all. And for life, it's just the opposite. You should change the neighbor count by 1 if it wasn't alive. If it was already alive, then don't change the neighbor count at all. So changes to those functions. And then also a change to our main function, where we're just going to start out with a new neighbor count matrix, which we'll initialize as all zeros in the same shape as our frame. And then we're going to go ahead and count all of our neighbors for the first time. So this is just going to populate our neighbor count matrix by going through each cell in the matrix and counting how many neighbors are in the frame at the given XY color coordinates. And we're going to put the number of neighbors that are currently at this location in our neighbor count matrix. And so then the other change we're going to make is in the next frame function. So in next frame, what we used to do was call the neighbor count function for each cell. What we're doing now is we're just looking up the neighbor count. in our matrix, and we're getting our rules. We're getting our function from the rules dictionary. So this will tell us whether we should make our next cell go alive or dead or stay the same. And then we're going to unpack what we get back from invoking that function into our result, what the new value in our matrix should be, and our increment. How should we change the neighbor counts? We should change all of the adjacent neighbors by this increment. So we set in our output frame, we set its XY color value to be the result that we just calculated. And then we're going to say if our increment isn't 0, then we're going to update all of the adjacent cells. We're going to add that to our updates collection. And updates is this default default dictionary. The default dictionary is such that if you try to access a key that has no value, it will use a default value, which is the result of just invoking this function that you pass to it. So of course, invoking the int function would give you back a 0. So when we try to get back a value that doesn't exist in this dictionary, it will start as 0. So let's look at the all adjacent update function. What that's going to do is just collect in our updates dictionary all of the updates that we need to make. It's just going to go through, similar to how we've seen in the past, we're going to go through -1 up to 2. For our x delta value, same thing for the y delta value. If they're both 0, that would mean we were considering the cell that we are currently on, change our x by 0 and our y by 0. Well, that means we're looking at the current cell, so just go ahead and continue. Don't do anything there. Otherwise, we're just going to check to make sure that it's in range. So x plus the x delta is greater than or equal to 0, but it's less than our max x value. And the same thing for y plus y delta. And so once we know that, we can put into our updates dictionary, rather we can increment our updates dictionary for this tuple, x plus x delta, y plus y delta color. We can increase that by our increment. So our increment might be +1, it might be -1. And so that's building the collection that I talked about here, our updates collection. And once we have that updates collection built, then we're just going to loop through all of the keys in our updates dictionary, and we're going to unpack them into their XY color. So basically get the coordinates of our neighbor count matrix that we should be updating. Then we're just going to say neighbor count sub x sub y sub color is going to increment by the value that we look up in our updates table. So we would increment the value at 0, 1 by 3. And that's going to keep our neighbor count matrix up to date. And so the result of calculating like this, this is profiling 10 frames. The way we used to do it, it took 113 seconds. The result here has dropped it down to about 26 seconds. And this is to produce the same number of frames. So you can see, like, basically we really decreased the number of neighbor counts and is alives. So we went from, we went from 1966080 neighbor counts to, looks like an order of magnitude less. So, like, this is kind of the 100% savings I was talking about. We just took out, we didn't make the neighbor count function itself any more efficient. We just said, well, we're going to neighbor count a lot less. I assume we also have a lot less is alive counts. Yeah, it looks like we cut that by an order of magnitude too. So rather than making these more efficient, we just did them less and saved a fair amount of time. So Another thing to keep in mind is that this is not quite a good comparison because it takes a lot of time to do to do kind of the initial processing. So reading the image, shrinking it to a 256 by 256, setting up our NumPy arrays. That takes a lot of time. And then doing the first frame is going to take the same amount of time with our new method and with our old method. And then doing subsequent frames will be a lot faster. So any given frame in the old method takes about 10 to 13 seconds. And with the new method, it takes maybe 2 seconds to do an additional frame. So it's substantially faster. Substantially faster to calculate like this. So we can, now we can start to generate like GIFs with 200 frames or hundreds of frames rather than being more limited like we used to be by having to wait minutes to get our answer. Now we can pretty quickly generate game of life boards with hundreds of frames. So one other thing I want to say here, you might notice, you might be thinking, how could we improve this faster? How could we make it even faster and get it down from 25 seconds? A pretty obvious place to look is how we could make these functions faster. So if we've already reduced them, like we've already stopped calling them as much as we can, we could think, okay, now we want to get that 20% performance gain. Now we want to, do something like that. And I think it's pretty reasonable to think that we could make isAlive a lot faster by replacing our numbers with Boolean values. So why does isAlive take so long? Well, it's because we've got to check, is this number greater than 127? So if all of our values were just Booleans, then that would be a much faster comparison. We would just say, is this true or false? And we wouldn't have to do a greater than, less than operator. So that would be one simplification to improve the performance. Another simplification, you might wonder why these functions are taking up so much time, and maybe we could save ourselves a function call and gain a little bit of time here. And that is almost certainly true. We could probably do that. But the performance gains aren't as obvious or aren't as huge. Even if we were to shrink all of these things to 0, we would now be saving ourselves about 5 seconds, which is pretty good. 25 seconds, cut it down to 20 seconds, but it wouldn't be as dramatic as our previous performance gain. And so you may be wondering, why would we want to use this function approach at all? And I think rather than just calculate whether or not they should be alive or dead without bothering to call into a function. And one reason why I like the function approach is because we can change what it means to live or die pretty easily. So our kind of naive live and die was just become 0 or become 255. But there we weren't really taking advantage of the fact that we're in color and we're using values that are more complicated than true or false. So a pretty simple way to start taking advantage of that would just be to say, okay, what does it mean to die if a cell is going to die? Well, we could reduce its intensity to 80% of its current intensity. Or if a cell is going to live, then we could increase its intensity by whichever is greater, either 10 points or 40%. And so now we can generate kind of more complicated GIFs or images. So this is still kind of following the game of life rules, but you can see, it's fading in, it's fading out. And rather than cells just kind of popping into being, they're kind of gradually growing here. So we can experiment with this and kind of generate maybe more interesting or more complicated games of life that really start to leverage some of the features of being in full color. And so now I guess finally the thing I'll say about Game of Life is I was showing this to my girlfriend and she asked me, what value does this have, or what can you do with this? And I think there are a lot of things you could do with it. So, I love the game of life, although I realize it's mostly for fun. But, I'm trying to imagine things I could do with it. One thing that I thought was a really cool idea that I don't think works, that someone told me about, was you could use it for compression. So if you just imagine, if you imagine the game of life, I'm hoping there'll just be one where I can click onto it. If you imagine the game of life, so like this is an example, and we send just these coordinates to someone. This is however many, maybe it's 15 cells. And then we tell them, and you should let this run for however many turns. You should let this run for 50 turns. And then it's going to give you a new message. So this is not great because it is creating fewer than I want. So we say, you should let this run for 100 turns. And it's going to produce more cells. Well, there are at least some configurations where it could produce more cells than we originally started with. So we sent you a message of 10 cells at the beginning. And what you plugged that into a game of life, and then created more cells than you originally had, and maybe you could generate a message like that. I don't think that would actually work. I think it would be impossible to it's not easy to click on all these cells. I don't think it would be really easy or practical to figure out how to compress messages that way. How to create the game of life board that, when advanced 100 turns, produces a state that could be interpreted as some message or some new thing. But it's an interesting idea, I thought. And then another thing that occurs to me, this I think is more practical, is right now we're applying the game of life to images and color. So we have 3 dimensions, basically. We have height and width, and we have color, RGB. We could just add one more dimension, time. And if we were to do that, then we could apply the game of life to video, not just images. And what I wonder about is, could this create a kind of interesting special effect? So if we can somehow incorporate time into our game of life board, we can create a kind of psychedelic blurring or like transition between images, where things will kind of like game of life morph from one thing to another instead of just naturally progressing in videos. So anyway, I'm kind of speculating here. I actually have a lot of ideas for what to do with Game of Life. And some are pretty far out there, I think have not been done before. And yeah, I'm interested in exploring it and going further with it. So if the Game of Life is something you're interested in, or if you're interested in this, let me know, leave a comment, click like. If you want to see some of my Game of Life experiments, then by all means subscribe. Generally, I'm solving LeetCode problems, and I'm updating my Game of Life investigations when I get around to it. So yeah, like I said, subscribe if you're interested. Thanks for your time. Bye-bye.